So, what we're doing in this chapter, chapter four, is we're moving past the review part of Econ 130, or just our basic microeconomics course where we talk about supply and demand, and we start to look at the first of the two um, actors, the first of the two focal points for microeconomics. One being the consumer, and then after we do the consumers, it's all about the producers. Now, the producers is going to talking about producers is going to take the majority of this course. Consumers, we're only going to be talking about it here in two chapters, chapter four and chapter five. Now, let's talk first about what does it mean to talk about consumers. So, talk about consumers means that we're talking about individual people. So, we're not talking about families. We're not. I mean, theoretically, we're not even talking about households. We're looking at individual people and exploring what their goal is. Their goal, which to some extent is to maximize their not necessarily happiness, but more so their satisfaction. Now, there's a difference about that, right? Because um, happiness, well, even as well as satisfaction, but happiness is going to be different between individuals. And there comes to be this point where what's the point of understanding one person's levels of happiness if you can't even apply those lessons and those insights to other people? So, what we also and then we also have to consider the fact that all consumers universally face constraints, and those constraints, even if it's not a monetary constraint, it's still a time constraint. So all these individuals face a constraint of some kind. So we need to work through these things. And we're going to do this primarily in this chapter with by talking about it through um, by talking about it graphically, but then we'll make some references to the mathematics, which appears more forcefully and more elegantly, in my opinion, in the appendices to this chapter. Okay. So, as we start to think about this a little bit further here, what we're working through here is this idea that um, individuals have certain tastes and preferences. I just actually read this really, just before making this lecture, I read this really um, interesting and somewhat sad article. Wondering, yeah, here it is. This guy spent his entire life, this guy right here, he's from Wisconsin. So there was like, oh, wow, he's from Wisconsin. So let's read about it. He spent about $1 million in his entire life building a $1 million stereo. The passion started when he was a kid, and record players were big things, and he just started to build it. Got these 10-foot high speakers here. It had this weird record player that has like all these different needles, and it costs like a bunch of money. Anyway, he had kids, but he spent all of his like free time working on this stereo. He divorced his first wife, got married again. His oldest kid never spoke to him again, um, and he built this $1 million stereo. And in the end, he had a form of like ALS, like what we call Lou Gehrig's disease. He then couldn't even he lost use of his like muscles, his arms, that he couldn't like put the records on the record player, that kind of thing. And in the end, when he died, the entire stereo as I was reading this long article talking about his life. The whole stereo itself sold for $156,800. And the problem was, no one, and it was said in this article here, is that, so look at this here, right? This part here. Most people didn't want what this guy precisely wanted, right? Like they'd want to build their own speakers, or they wanted a particular kind of sound that this guy, didn't build. Now, I'm making this lecture now shortly after having read that entire article, and all that it makes me think of. Well, outside of the fact that he could have spent his money on other things, in my opinion. But it's also just not my opinion. It's the fact that it's an individual taste and preference. Just think about what we all do that, in some sense, what we spend our money on that's somewhat unique to ourselves. I mean, there was a time when I was younger, in my 20s, when I spent a lot of money on shoes. I don't know what it is with men and buying shoes in their 20s, right? But, dude, I had a lot of nice, really nice shoes. But I got to a point where I got married and had kids and I have bills, and I realized, geez, why am I holding on to these shoes? I mean, I just go to a job. I care more about taking care of my kids now and making sure the mortgage is paid and all those kinds of things. So I've now sold my shoes and I sell them on eBay, and it looks like I'm selling them to a lot of men in their 20s. Size 12 shoes. In this case, now my individual tastes and preferences have changed. But also though too, right? You get to know people who are in my age group, right, in their mid 40s, and they still collect Teenage Mutant Ninja toys, plastic toys, and they have like a room in their house filled with those toys. Typically, they don't have kids. Sometimes they're married, but most of the time they don't have kids. And right, so there wasn't something that prompted them to change their taste and preferences. Now, what does that mean? Are we trying to say here, make a generalization and say all men in their 40s with kids tend not to overspend on shoes? No, we're not really even saying that. But we are saying that just people in general change over time. And that they form a particular set of tastes and preferences that are unique to themselves. And combined with that, not only do they face these tastes and preferences, but they're also subjected to constraints. Constraints on their time, budgetary constraints. And that what people do is they focus their time, they orient their time around maximizing their satisfaction that they get from consuming things subject to the constraints. So what that means for us here is that we're going to have a function that we can, a mathematical function where we can describe people's tastes and preferences. We're going to be able to graph out these tastes and preferences. And for the constraints, we're also going to have a function, and we're also going to be able to graph them out. So we can call this kind of step 1. Step 2 is the constraint. And in step 3, we are maximizing that satisfaction subject to that constraint. Now, if the mathematics of this really interests you and you're thinking even mildly about graduate school, you'll want to make sure you read the appendices to this chapter. I'm not requiring them, I'm not assigning them in this course, but I wouldn't be doing you any. I wouldn't be doing you any favors by telling you don't look at the appendix. If the appendix appeals to you and you really like it and it makes a lot of sense, then you should really strongly consider getting your master's in economics. If it really bothers you and it doesn't do anything for you and it doesn't interest you and there's no way you could ever think about it interesting you, then you might not want to consider graduate school. It's a good litmus test, at least, of things. Okay, so let's start to talk about when we're trying to understand consumer preferences, both in terms of the mathematics and the graphics, what do we know to be true? Well, one of the things that we are going to know to be true is that preferences have completeness. Now, what does it mean to have completeness? To have completeness means that every bundle has a relationship. Sorry, it's not my handwriting, it's the sensitivity of this pen here. If we had two bundles, now what do we mean by a bundle? A bundle is just a collection of goods. I know it always sounds weird when I use this as an example, but it's the one that makes most sense to me. You know when you look at those pictures of like a Thanksgiving cornucopia. Sorry, I misspelled it. But see, it's like a cornucopia. It's filled with all these various pumpkins and squash and whatever. But it's filled with a bunch of different things. That's what we mean by a basket of goods. Just imagine something containing a bunch of other things. And so if I were to present two of these bundles to you, one of three relationships is either going to exist. Either that you're going to prefer A to B, that you're going to prefer bundle B to bundle A, or that between A and B, you are indifferent. So one of those three relationships have to exist. There has to be a choice that can be made between the two where you have enough information. Okay. So completeness is our first property. Then we have our second property here, which is transitivity, or just a fancy way of saying that everything is logically organized. If, as it tries to describe here, if A is preferred to B and B is preferred to C, then A must be preferred to C. And so this is just implying that they're logically consistent. And then C, I don't know where they go from saying fancy words to not. Yeah, you could think of it as more is better. I just refer to it as non-satiation. More is always better. Always, always, always. More is always better. As long as the thing is a good, something that increases your consumption. There's not many things in reality that meet this. I mean, I like candy as much as the next person, but I don't know, some point where I just don't want it. It's just there has to be in reality there have to be some limits, but we're not going to presume that those exist here. We're just going to say that more is always better. Now, graphically, then, if we want to think about this, what we would start to do is we would start to map these out. And what we're going to map out is a point where things are indifferent, meaning we're going to map out the bundles where individuals are equally satisfied or happy with each of those bundles. And we're going to do this in a graphical space called an indifference map. Now, how does this look? So just look at the graph to begin here on the left side. Okay, let me just pause for 1 second. Sorry. Okay, so what we're doing with this graph on the left is we're just measuring, we're just placing a bunch of bundles. So you could imagine that on the side here, let's see here, goes to F. Okay, so you could imagine we could have a listing of all the various bundles that exist. So bundle A, B, C, D, E, F. And in this, we would have something that lists the number of burritos and the number of zas. That's the cool word for pizza. Not anymore, but I'm going to use it because you're forced to listen to me. Okay, so you could imagine here, that bundle D, for instance, has 10 and 15. 10 burritos and 15 zas. Right, and we could go down this, up and down this list, right, and just be tracing these all. I don't want to mess things up too much here, so I'm just going to get rid of that for now. Okay, so based on our property that we already know exists of non-satiation, or more is always better, then we know that C is preferred to D, right? Why? Because C has just as many zas as D, but C has more burritos than D. So C, why did I put 10 and 15 here? Sorry, it's 10 and 15 here. This has 15 pizzas, but it has, looks like 25 burritos. So we know how C and D, we know what the relationship is between the two of them. Now, we also know, for instance, that between E and D, that E is preferred to D. Okay, and how do we know that? Because E has more of both goods, 15 and 25, than D, which has 10 and 15. But now, with E as our focal point here of 15 and 25, here's the question that we're trying to answer here. What is the relationship between E and C? We know that a relationship has to exist based on the first characteristic of these curves, which is completeness. So we know some relationship must exist. We just don't know if it's E is preferred to C, E is not preferred to C, or basically C is preferred to E, or if E is indifferent to C. We don't know. And our knowledge of non-satiation is not enough to tell us because C has more burritos but less pizzas. So we would need to have some more information to be able to say what the relationship is between E and C. So based on non-satiation, we know that D is not preferred to E, or that E is preferred to D. We also know that F is preferred to E. Why? Because F has more of both goods. So also based on non-satiation, or more is always better, we now know the relationship between E and F and E and D. But we don't know the relationship between E and C because C has, again, more of one good but less of the other. And we also don't know the relationship between A and B, where A and B have more of one good, in this case Zaz, but fewer burritos. So what is that relationship? That's where we need the graph on the right. So now shift your attention to this graph on the right, and you'll see that a line has been drawn. That line is called our indifference curve. And it's drawn mathematically, it's deduced mathematically based on what the function looks like for the satisfaction. But what it does, if we just look at this line generally, what it does is it traces out all the points, it combines all the bundles that are generating the same level of satisfaction, the same level of happiness. So in this case, the way that it's drawn, E is preferred, E, A, and C are indifferent to each other. And as we look on the next slide, bundles on higher indifference curves bundles on higher indifference curves are preferred to bundles that are on the lower ones. So basically, we prefer F over C and E. We prefer F, C, and E to D. Higher indifference curves are preferred to lower indifference curves. So then, restating what the goal of the consumer is. The goal of the consumer is to consume on the highest indifference curve, or the indifference curve furthest from the origin. And again, these indifference curves are deduced based on mathematics. So here's a good statement now of these facts about what indifference curves look like and what an indifference map, where you would have the quantity of one good and the quantity of another good, is that you would have these indifference curves where there's higher levels of utility of satisfaction the further you go from the origin. Every bundle has an indifference curve going through it. Indifference curves further from the origin are preferred to those that are closer to the origin being right here. These indifference curves do slope downward. That's just because of the very nature, the shape of the demand curve, and the fact that individuals do start to get diminishing marginal satisfaction from each good, which we'll look at here shortly. But the other one here is property number 3, which is that indifference curves cannot cross. And the reason why is because it would violate non-satiation, or more is always better, and transitivity. So let's say that this was true, that this is the way that this looked, where they were crossing. Then A would be indifferent to B. A would be indifferent to C. And then based on transitivity, B would be indifferent to C. But that can't exist because B has more of both goods than C. So if indifference curves crossed, we wouldn't be able to hold these characteristics of indifference curves of non-satiation and transitivity. Other things about indifference curves that can't exist, besides them being crossing, is that they are not upward sloping. Why? Is because it would violate this concept of diminishing marginal utility. What do we mean by that? This person here is consuming more pizzas and they're getting happier as they consume more and more pizzas. Certainly, they should be happier with having, well, I guess you could even say here. But how could you be, how could you prefer to have one bundle that has less of both to one that has more of both? So we're going to be violating our concept of diminishing marginal utility and of non-satiation, of more is always better. B should be on a higher indifference curve, not on the same. And also indifference curves are thin. This indifference curve is too fat. It needs Ozempic because A and B here can't exist on the same indifference curve and be indifferent to each other, even though B has more than A. So I don't know why they're giving you this as a question. It's a dumb question because we just described it. Now, you'll notice that when I was looking at this upward sloping feature, I was talking about both it being upward sloping, but also having kind of long tails here. And I talked about this diminishing marginal utility. If you heard me saying it, you might have thought for a moment, well, what is he talking about? Well, what we're talking about here with the marginal rate of substitution is you're talking about how much additional satisfaction or utility you get from consuming one more unit of the good. Or, said another way in terms of marginal rate of substitution, how much of the other good would you have to get rid of in order to be able to consume more of the other good? If this is an XY space, where we have quantity of X and we have quantity of Y and an indifference curve that looks like this, then I'd be looking at how much Y am I giving up to get more X. And what you'll see is that the slope is changing along the curve. That the sacrifice here, you'd be willing to give up a lot of Y for just a little X. And over here, you're giving up just a little Y for a lot of X. So why is it changing? Well, it has to do with the sheer amount of the thing that you have. So the fact that at let's just call this point A here. At point A, I'm in a situation where I don't have a lot of X, but I have a lot of Y. That kind of person would be willing to give up a lot of the Y because they have so much of it, just to get a little bit of X because they have nearly none of it. And that changes over here where they're got so much X, but not a lot of Y. Where they, in this case here, you'd have to get a lot of X in exchange for giving up just a little bit of Y because you have so much of it. In this case of X. And we see this here. That one way to simplify this discussion would be to keep the denominator the same throughout. So let's keep it as just 1. Then what we can see, if we want to describe this in words, that as we move from left to right, so as we move from left to right, the way we would understand this is that we have to give up less and less of Y to get X. If we're moving from right to left, that's a cool color. As we move from left to right to left, then as we move from right to left, we get more and more Y for our 1 unit of X. It changes because of that law that you were introduced to, at least in principles. Because of that law, of diminishing marginal utility. That as we consume more and more of the product, we get less and less additional satisfaction. It means then that the indifference curves do need to be convex to the origin. They can't be concave to the origin because if they were concave to the origin, that would then violate the law of diminishing marginal utility. And so again, these indifference curves do need to be convex to the origin. Just as we see a law of diminishing marginal utility, we also again have that diminishing marginal rate of substitution between the two goods, which means that on the left-hand side, our indifference curve is very, very steep, and that it gets flatter and flatter as we move from left to right. I would actually add that there are 3 special cases Let's start with the first two here, at least that have slides. Let's start with the fact that we can have perfect substitutes. These would be goods where consumers are indifferent between the two goods because they fulfill exactly the same need. And then we could have perfect complements in consumption. And this would be where you only consume the one good when you're consuming the other. In the case of the perfect substitutes, you'll know that the MRS is constant. What would an example of this be? I don't know. Like, if you were to give me coins, I would always accept 2 nickels for a dime. Even the burden of the extra weight or whatnot, I don't care. I'll always take 2 nickels for a dime. I don't necessarily agree with this. I actually seem to like Coke more than Pepsi. But in this case, this person is saying that they're indifferent between Coke and Pepsi and that they're willing to consume one for one. Okay, so these perfect substitutes have a linear indifference curve. Okay. And these perfect complements have what are called the Leontief indifference curve, named after a person named Wassily Leontief, who was an economist after World War II at Harvard, and who was colleagues with an economist whose son is actually a historian here at University of Hawaii. But Wassily Leontief from Harvard, he described these perfect complements in consumption would be that, I don't know, in this case, this person wants ice cream and pie, and they want 1 scoop of ice cream with 1 slice of pie. And the additional scoops of ice cream don't make them any happier because they need to have that exact combination of slice of pizza and ice cream. And only when it goes from 1 to 1 to 2 to 2 are they happier. Otherwise, these scoops of ice cream are just excess. So these have, again, L-shaped indifference curves, or as I would like to call it, Leontief indifference curves. Most products are imperfect substitutes. Somewhere between those two extremes of perfect substitutes and perfect complements, which is what we have here. I want to eat food, right? And you could say I'm in the mood for X, right? Or I'm in the mood for pizza. I'm in the mood for burritos. But if I tell you there are no burritos, unless you're 2 years old, you'll probably accept pizza instead. I say this because obviously I've got lots of kids who are irrational to me because they don't fit this model. Now, what about between things that are not really substitutes for one another, at least in their use? And that would be food and clothing, right? So we can imagine that the shape is a little bit different and that people need basic amounts of food and clothing. But that once you get to greater amounts, they're still not going to intersect each other, but the shape is going to somewhat change. Because now you can notice that a person just has more than 1 shirt, or more than 1 pair of pants, more than 1 pair of shoes. They have some variety. And so that variety is going to influence now and alter the way in which they make those trade offs between food and clothing. Now, we need to actually start looking at the math of all this for this to make any sense. So that kind of concludes our graphical description of this. So what we need to do here is we need to start looking at this notion of what is utility. So utility is going to be a number that is used to describe satisfaction. It's going to be the number we use to rank order the bundles of goods. So this is very important. And sometimes I think that books and whatnot understate this situation. Utility numbers, like let's say my utility number is 50. That does not mean that my happiness number is 50. All that it does is it rank orders. This is an ordinal number, not a cardinal number. It's an ordinal number that tells me my level of satisfaction relative to some other bundle. But the way that we get to that utility number is that we get to it by having a utility function, which is going to be some mathematical way of describing this. In this case, this is to the 1/2 power, or to the square root. But not every utility function is going to look the same. But in this case, the utility for pizza and burritos is equal to the square root of the quantity of pizzas and burritos. So if it were me making the slides, but it's not. If it were me making the slides, I would have said this a little sooner, because obviously I said it to you in slide 22 rather than 23. But this just reiterates that utility numbers are ordinal and not cardinal. Meaning, again, utility numbers just help us rank order things, where a bigger ordinal number is just better than a smaller ordinal number. But an ordinal number that's 50 is not twice as good as one that's 25. We just don't know that to be the case. All that we know is 50 is better than 25. Money is a good example of something being cardinal. 50 cents is twice as much money as 25 cents. Now, what we're trying to stay along an indifference curve is that the utility number is constant. And what that means for us graphically is that we try to graph this out. Is that for my level of, for my quantities of pizza and burritos, we can start to graph out across all those with, in this case now, partial burritos and partial pizzas, that we can measure out all of the combinations of burritos and pizzas that mathematically equal the same utility number, ordinal utility number. And so we can understand it spatially in these kinds of ways. But what's nice about having a function is that we can then take the first order partial derivatives of that function, which is done in the appendix and which we will do in preparation for the problem set. What I just said there, for those of you who've taken Calculus 1, is what we would call the first order partial derivative, which is the slope of the utility function as we hold the quantity of one good constant. And that what we can essentially see here is that if this is my utility function, that my marginal utility is going to look like this, right? Where I consume more and more pizzas, I get less and less additional satisfaction, right? So this is my, here, I don't need Copilot. This is my law of diminishing marginal utility. And that my marginal rate of substitution is the slope of that indifference curve. Meaning that if I have quantity of x here and I have quantity of y here, that the marginal rate of substitution is going to be my ratio of my two marginal utilities. And because it's downward sloping, it's going to be negative. So that would mean, like, if I had a utility function that looked like this, that the first order partial derivative with respect to x would be 2y, and that for mu would be 2x, which, putting it into this function here, I mean it'd have 2y over 2x, which just would equal y over x. And that would describe my slope along my changing slope along the indifference curve. So the marginal rate of substitution is my slope of the indifference curve. And what we have to counter that to is some limitation. And that's going to be our budget constraint. Okay, I'm going to pause here shortly. Okay, so with slide 30, we kind of get into step 2. Just to remind ourselves of where we're at here. In step 1, we understood that the consumer is trying to get on the highest indifference curve. So we described what that indifference curve, how it's drawn. We described what the slope is of the indifference curve, the slope being the marginal rate of substitution. And that our goal, again, is just to be on the highest indifference curve. Now, here, what we're doing with starting with slide 30, is looking at the idea that what stops us from being on the highest indifference curve is some sort of constraint. And that, for most of us, yes, time is a constraint that we all have, but it's a little bit easier to describe this in terms of the budget constraint. The idea here being is that we have prices of goods, we have a budget of money to be spent, and that we can only then spend so much on the goods. Given the budget that we have, we can only buy so many goods. And what it does is, another way to see it or to understand it would be, is that it creates an opportunity set. What is affordable versus not? Affordable versus unaffordable. And so the budget constraint is pretty simple to understand here. You would have your price of burritos times the quantity of burritos plus the price of za times the number of pizzas, and that would equal your total income. So here we have now an equation for the budget constraint. And again, we would know what's affordable versus not affordable. And this shouldn't be too difficult to solve because essentially what we could do is note that we could try to understand our quantities. We could try to understand our quantities in terms of the income and the prices of the other goods. So here, they're going through a step that I wouldn't necessarily think is that important. So you can follow along with the math as you want, but they're obviously subtracting the allocation here for pizza from both sides, leaving me with P subscript B, price of burritos times the number of burritos, equaling my total income minus the price of pizza times the quantity of pizza. Because I want to solve for the quantity of B, the burritos, then I'm going to divide each side by the price of burritos. Which means that the slope of the budget constraint is the price of the good on the x-axis over the price of the good on the y-axis. And it's negative again because it's downward sloping. So again, what it does is it gives you, with the restatement of the budget constraint, it would get you another way that if I told you 3 of the 4 unknowns, you could solve for, in this case, 3 of the 5 unknowns. You could solve for the number of burritos in terms of pizza. And so this we can see here is that if I have a certain budget amount, $50, and a certain level of prices for the 2 goods, 1 and 2, that we have a bundle where it represents the extreme, only eating burritos at $2 a piece. And another extreme where they're only buying pizza and no burritos, and then something in between. And again, it creates this what they want to call an opportunity set, but which I'll just call anything below the budget constraint as being affordable, and anything beyond the budget constraint being unaffordable. So these are all of our possible options, are the points that lie below the indifference curve. Or sorry, below the budget constraint. The slope, again, as I already said, price of good on the x-axis over the price of the good on the y-axis. Pizza being on the x-axis, burritos being on the y-axis, price of pizza over the price of burritos. The other term, instead of just calling it the slope of the budget constraint, the one way you can see this is at the slope of the budget constraint is the price ratio. Or you could simply say that it's the marginal rate of transformation. Just another term for it. And so we can solve here. If you're given prices and a quantity, you can then begin to solve for things. Solve for the optimal quantity of, in this case, water, and then the optimal quantity of all goods other than water. And in this case here, if you have a quota, it can start to create a situation where consumers aren't, in this case, able to buy more than a certain amount, which then creates a series of problems because you're going to limit what consumers can do with their money. That they can't buy more, in this case, than 2,500 gallons of water a week. Now, what becomes cool about this, though, is that we can now start to look at what happens when the price of a good changes. When the price of a good changes, what we already knew from the last chapter, just a very simple basis, was that as the price of a good changes, we move along that demand curve. But in terms of the budget constraint, if we lower the price of the good that's on the x-axis, the budget constraint becomes flatter. And that we can see right here is that the budget constraint is becoming flatter as the price of pizza goes down, or the reverse, which is kind of what this graph shows here, is that the price of the good on the x-axis goes up, the budget constraint becomes steeper. Now, if the price of both goods change, or if my income changes, the budget constraint shifts out if the income is increasing. So in this case, income is going up. I can now just afford more of all goods, even if the prices are not changing. And this just highlights here what I just said here. If income doubles or my prices fall in half, the impact on the budget constraint is the same, which I just kind of already implied here. Either my income doubled or the price of both goods fell by half. Now, this begins step 3. Again, just to review. Step number 1 was preferences with the indifference curve. And that indifference curve had a slope of the negative ratio of the marginal utility of the good on the x-axis over the marginal utility of the good on the y-axis. Then in steps 2, we had the budget constraint, where the slope was this was the marginal rate of substitution. Here we had the marginal rate of transformation, which was the negative ratio of the two prices, the price of the good on the x-axis over the price of the good on the y-axis. Step number 3, which is what we're working on now here on slide 42, is that constrained choice. What does it look like for me to be maximizing my utility subject to my constraint? Putting everything in the same space, it looks something like this. So with just step 1, I wanted the highest indifference curve. So in all these ratios, I just would have picked F, because F is on my highest indifference curve. But the problem with F is that it's unaffordable. The problem with D is that it's affordable, but it's not on the highest indifference curve. So I want to be on the highest indifference curve, just subject to my constraint. So what I want is the slope of my indifference curve to be equal to the slope of my budget constraint. Which is what's happening here at E. At C, what we can see here is that the slope of the indifference curve is steeper than the slope of my budget constraint. So at C, MRS is greater than MRT. And here at A, my slope of my budget constraint is steeper than the slope of my indifference curve, or MRT is greater than MRS. But at E, MRS is equal to MRT. And I'm on the highest indifference curve. Subject to the constraint. It's both affordable and on the highest indifference curve. And that's what we see right here. That the slope of my indifference curve, my MRS, is equal to my slope of my budget constraint, my MRT. And we're going to do problems related to this, so we're almost there. But the way that these will be set up mathematically is that you'll have a utility function. We will find the first order partial derivative, which isn't that difficult to do. We're not going to do anything that intense here. And then you will have the ratio of the prices and the budget that can be that would exist. And what we can do is we can find these things. So let's actually find them here. So if we graph this out where we have quantity of jelly here and quantity of peanut butter here. Again, our goal is to find this point here. So if U equals Jn, and how did I know this? Because the first derivative with respect to J, that would mean that the J no longer exists, and so it's just going to change by N. The first order partial derivative with respect to N is going to be just J. So now I have N over J equaling the price of jelly, which is 5, over the price of peanut butter, which is 10. 10N equals 5J. So now what I know is that the optimal ratio must be two peanut butters to one jelly. Okay, now why do I need this $100 income? Because now what I'm going to do the N again standing for jelly, is that now I know that this is 100 equals price of peanut butter is 10 B. Sorry, I'm confusing everybody by going between N and J here. Sorry. See what I did there? The goal here was to remove one of the unknowns so I could actually solve it. So what I did is I substituted for j 2n. Because now, and then 5 times 2 is equal to my jam. So now I've got 10 jam. So there's my optimal. That's my optimal number of peanut butter and jelly I should consume with $100 to maximize my income. These are the kinds of problems that we're going to be solving on the problem set as well as on the homework. And we followed these steps. And that it would create a situation where we had normal consumption levels that were affordable. Now, we do sometimes get an extreme situation known as a corner solution. So what you can see here is that the only point at which the consumer even gets close to having the slope of their budget constraint equal the slope of the indifference curve is at the extreme. So only when the person is eating nothing but burritos is the person anywhere near to being satisfied. These corner solutions do cause some problems because what if even that's not enough? And it just creates an extreme addiction, if anything. That this product is too high. We tend to see these corner solutions exist when the products have when there are perfect substitutes. So what the book starts to describe here is this active ingredient, sodium hypochlorite, where individuals are substituting between those two goods that generally fulfill the same needs, and what will that person buy? And as we bring it out here, what we see is that with the budget constraints and the indifference curves, that the person, if we're talking about the generic brand, will only consume the extreme of buying nothing but the generic brand when the price is $3. And then when the price goes down to $2, that each and every one of these points is equally okay. Why is that the case? Because in this case, what we see is that Clorox costs 3 times as much as the generic, but it's only twice as powerful. So the person, as a per dollar basis of the power of the sodium hypochlorite, would buy nothing but the generic because they get to pay a third less, but it's only half less powerful. When the price goes down to $2, though, now it's twice as expensive, but it's twice as powerful, which would mean that all of the points are now equally satisfying. And again, now as we kind of get to the closing slides here of this chapter, we're just looking at some more extreme shapes here. We could look at indifference curves. Again, one of the problems that we would have is if the indifference curves are concave, that the person could be consuming, that we would have 2 points where the person would be setting their marginal rate of substitution equal to their marginal rate of transformation, points E and D. The problem would be is that a person would obviously prefer I2 to I1, indifference curve 2 to 1, because 2 is further from the origin. So again, this is our reason why our indifference curves are convex to the origin rather than concave to the origin. And we'd even run into this problem with the graph on the right where our indifference curves are concave and convex, because again, you could create a situation where a consumer has two optimal points rather than one optimal point, which they should have at just E. And then you get a situation where, as we start to think about how do we apply what we're learning here to the real world. Well, one of the things we could look at here are food stamps, or what we would call SNAP or EBT. So, although this has grown since 2019, you have a little over 10% of the people receiving food stamps, of about $130 a month. Now, food stamps can only be used on non-hot foods, but what they do is they force then the person to buy only those foods, right? So you can't use food stamps on toilet paper, even though you might need toilet paper. You can't use it at a restaurant, even though it's the same kind of food. It's a restriction. Now, the question that's sometimes raised here is, would it be better off to just let people use the money as they see fit? Why are we forcing them to spend the money on food? Right? And we don't actually care what they spend the food stamps on. For instance, what kind of food, right? So I could just be buying candy with it, and there's no restriction. I could be buying just processed food, or I could be going to Whole Foods and just buying organic stuff. Not as much, I guess, but right. So there's no real limits on things, but it has to be used on food. But here's what it does: is it creates a budget constraint for the family that now looks different. If the person is being given $100 that can only be spent on food, then the budget constraint is C, E, and then down to the x-axis, because $100 has to be spent on food, and then it's the rest of the money that the family earns. If instead it was just a cash subsidy where the person could spend it on whatever they wanted, then the budget constraint would start here and go down, allowing that person instead to buy F. What's important for this here is that by creating food stamps that can only be used on food, the optimal point, yes, that looks messy. The optimal point becomes point E. But at E, the marginal rate of transformation is greater than the marginal rate of substitution, meaning E is not an optimal point. Instead, point F would be the optimal point, allowing that person to be on a higher indifference curve. But in some sense, that higher indifference curve is not possible because of that restriction placed on what food stamps can be used for. What else do I want to say? I just don't want to bring up this chapter too long here. I think we're just going to leave it at that here, just to keep the lecture under time constraints here. Okay.